When I say that this video is probably the most important programming video you're ever going to watch, it's partly because what I'm going to tell you is distinctly a minority position among programmers. Probably 5% or under programmers will tell you that definitively object-oriented programming is just not a good idea, and in fact is going to lead you astray. Maybe you'll have another 20-30% of programmers who will hem and haw and say that it has some virtues and some weaknesses and it might be better applied to some problems than others. I'm not telling you that. I'm telling you definitively, no, object-oriented programming doesn't fit any problem and you shouldn't take it seriously. This is almost certainly not what you were told in school. If you attended a programming course in the last 15 years or you read most educational materials about programming, the pervasive default assumption is just, well, object-oriented programming is the right way to go and it's just a settled matter. So I reiterate, this is probably going to be the most important video you watch about programming because it's going to tell you something you're not going to get from a vast majority of other sources. First off, I'm going to try and make clear exactly what I'm complaining about and what I'm not complaining about. And then I'm going to try and explain, well, what is object-oriented programming really? Because if we don't nail that down, it's almost impossible to criticize. And then I'll try and account for, well, if object-oriented programming isn't good, why does it dominate the industry? That's kind of an important question, actually. And then I'll actually get into, well, why does object-oriented programming not work? What's bad about it? And then lastly, if I'm telling you to not program in an object-oriented style, then what do you do instead? What is the alternative? It's called procedural programming, but what does that look like exactly? So what are the problems with object-oriented programming? Well, first off, the problem is really not classes per se. That is, I think it's actually possible to program occasionally with classes in a way that's fairly benign. I don't think it's particularly beneficial, but for aesthetic reasons, it might seem more pleasing to have an explicit association between certain functions and certain data types. Doing this pervasively, though, as I'll make clear, is a really bad idea. That's where everything goes wrong, is when you try and shove every function of your code, every behavior, into an association with a data type. That leads to disaster. Secondly, I don't think the problem with object-oriented programming is about performance. I recommend you watch this talk by Mike Acton called Data-Oriented Design in C++. He makes some very interesting points and provides some insight into that world of programming, which most of us don't do. But I think he overstates his case. Fine, there's a lot of software out there that should be written with much more regard for performance, but I think there's tons of software that just really doesn't apply. You'll also hear complaints about excessive abstraction from generally the same people like Mike Acton. And again, here I think they're overstating their case. I think abstraction is actually a worthy goal. In practice, most abstractions aren't good. It takes a long time to develop good ones. And as I'll explain, a major problem with object-oriented programming is it does tend to produce abstractions that aren't any good. That's the real problem, not the idea of abstraction itself. Another interesting talk to watch is one by Abner Coimbray called What Programming is Never About. And the thing which he says programming is never about is code prettiness, how code looks, aesthetics. His main point is that programmers typically focus too much on surface concerns about their code, rather than stuff that really matters. I think, though, he actually simply misstates his case, or rather his thesis doesn't really follow from his arguments, which are generally valid. I think when really pressed, he would admit that elegance, simplicity, flexibility, readability, maintainability, structure, all these things you might file under code aesthetics, I think he would admit actually do matter. But I think the more accurate way to spin his point is that these surface-level virtues of code are good things and actually important, but object-oriented programming and abstraction-heavy programming in general fails to deliver them. In fact, it provides just the illusion of these things. Object-oriented programming is sold on the basis that it supposedly provides these things, but particularly simplicity and elegance, it actually makes things worse. Lastly, be clear that I'm pushing procedural programming, not necessarily functional programming, which is a different thing, as I will make clear in a moment. I happen to think that functional programming actually is the future of higher-level code. I think it may actually be the default way we program at a higher level in 10 years from now or something. But there are serious efficiency problems that make functional programming not really viable in certain domains of programming. And so my message is, whether your code ends up functional or imperative, that's a separate matter. Regardless, your code should be procedural rather than object-oriented. So it's a good time now to make clear exactly what are the competing paradigms of programming that we're really talking about. There are four main possibilities. Your code can first be both procedural and imperative. Procedural meaning that you have no explicit association between your data types and your functions, your behaviors. And imperative meaning that we just mutate state whenever we feel like it. We don't have any special handling of shared state, which can cause problems as your code gets larger and larger and more complex. But in procedural and imperative programming, we just cope with the problems as they arise. And you can think of this style of programming as being basically the default. It's the obvious way to get work done. So this is really how all programming was done in the early days of computers. But then starting in the 60s, as programs got more and more complicated, people began thinking about, well, how do we solve this problem of shared state? Because it really can get out of hand. And so we got two major prescriptions on how to handle the problem. One of these prescriptions says that our code should be procedural, yet functional, meaning that all or most of the functions that make up our code should be pure. They should not deal with state. And so programming in this style, we would tackle the problem of shared state by minimizing state, trying to get rid of as much of it as possible. The other prescription people came up with said that our code should be object-oriented and imperative, and the strategy here is that we simply segregate our state. We take the state that makes up our program, and instead of sharing it promiscuously, we try and divide and conquer the problem. We package it into these encapsulated units that we call objects, and objects contain other objects and so forth, and that's how we conquer the problem. And these two prescriptions are actually orthogonal to each other. We can do both the functional business to minimize the amount of state which our program deals with, and then whatever state is left over, we can then segregate into separate units of encapsulation. And in fact, I think this combination approach may actually be the ideal way to structure programs, at least in terms of high-level code, where we don't care so much about efficiency. As I'll explain, I think segregating state is actually a valid strategy up to a certain level of detail, a certain level of complexity. And so if we first minimize the amount of state which our code deals with, it then becomes a viable strategy to segregate the remaining state. You may have noticed in my definition of object-oriented programming that I said nothing about inheritance, and that is because inheritance is simply irrelevant. No one defends it anymore. Even people who advocate for object-oriented programming will very, very commonly these days tell you to be very, very careful in using inheritance, or maybe not to use it at all. And so it's not really pertinent to any argument about whether object-oriented programming is good or bad. For similar reasons, I didn't say anything about polymorphism in my definition, because polymorphism, really good or bad, isn't exclusive to object-oriented programming. You can have procedural code that is polymorphic, and in fact, even more polymorphic than is typically available in most object-oriented languages. So it's really not part of the discussion as far as I'm concerned. When I complain about object-oriented programming, I'm really complaining about one idea: encapsulation. Encapsulation does not work, or as I should qualify this, encapsulation does not work at a fine-grained level, which is the core of what object-oriented ideology prescribes, that we need to take the state of our programs and divide and conquer that problem by chopping it up into tiny little pieces. That is the nature of object-oriented code, and it doesn't work. It leads to madness. Before delving into why object-oriented programming doesn't work, it is important to address this mystery of, well, if object-oriented programming isn't so great, why does it now dominate the industry, and why has it done so for almost the last 20 years? I've heard it sometimes suggested that, well, this was an imposition of management. Management wants interchangeable developers so that it can have a cookie-cutter assembly line development process. Hence, business types were really enthusiastic about object-oriented programming promises about code reusability and compartmentalization. It's a theory that sounds plausible to me, but the main sticking point is that object-oriented programming doesn't actually deliver these promises. You'd think people would have noticed sometime in the last 20 years, yet they seem not to have noticed. I'm also skeptical of the idea that management actually really inserts themselves in these technical decisions that often. I suppose once, say, object-oriented programming was well established and that became the pervasive norm, then yeah, sure, management would push towards doing what everyone else is doing so that they can draw from the larger talent pool. But otherwise, aside from pushing engineers to just go along with the legacy system and not rebuild everything, I just don't think that many business managers really care that much about technical decisions. I'm much more inclined to think that object-oriented programming is something that programmers did to themselves, and the question is then, well, why? I think a big part of the answer simply comes down to Java. When it was first introduced in the mid-90s, Java seemed like a welcome reprieve to many programmers. Compared to the alternatives, Java seemed really simple. For example, on the PC, this is what application development looked like. You had to use the Win32 API in C, and not only did programmers have to concern themselves with memory management as you do in C, but on top of that, Win32 just doesn't feel like the C that you would learn from books. It's not what you would learn from K&R. It's not what you would learn in school. It's all this excess macro-heavy stuff on top that is really mystifying. Even the tools you would use to write C programs on a Windows platform, the Visual Studio tools, wouldn't be the same as what you would learn in university probably, where you probably had a Unix system and that's what you learned. So it was already this platform with a quite high barrier to entry, But then also in this period, it was undergoing this ugly transition from Win16 to Win32. And so you can begin to see why programmers were desperately looking for some way out. The only real alternative at the time in PC programming was Visual Basic, but that was another effective Microsoft platform you're locking yourself into. And I suppose otherwise you might use Pascal or Delphi, but that platform had its own issues. And so it shouldn't be too surprising that when Sun Microsystems came along and said, here's this free thing that everyone can use across all platforms, that got people's attention. And Java had other things going for it. It certainly seemed more accessible, just in terms of like its naming conventions. For example, you look at the Java APIs and you see things like file input stream, which is not cryptic at all. Yes, there are definitely issues in how abstracted many of the APIs are and having to derive base classes to use the APIs and all that nonsense. But on first glance, on surface inspection, it certainly seems like a friendlier system. It's not like Unix where you have stuff like IOCTL, which is you're supposed to know is input-output control, and other really horrible abbreviations. And then Win32 had the same thing. LPCTSTR stands for, long pointer to a const tchar string. So even if you know what a tchar is and a long pointer is, you're stuck in this world where everything is cryptically abbreviated. And it's just this goddamn puzzle that you have to figure out at every step. Java came in and said, no, we don't necessarily have to program that way. We can write real programs that don't have to be horribly cryptic in that way. And then Java took things too far in the other direction, but that's, again, we'll get to that. Java also smartly had the C-like syntax, the curly brace syntax. So superficially, at least, it seemed familiar to programmers from C and C++, and it seemed like real programming. It has curly braces after all. And then the whole compilation to VM bytecode business was, again, very alluring to programmers trying to escape their platform headaches. And then Java also offered some very basic niceties like proper namespaces without header files. For Christ's sake, we still have to deal with header files to do our real programming in C and C++ at least 20 years after we should have ditched them. If for this one thing alone, I think it's worth giving Java some credit. It mainstreamed programming without header files. And then, of course, also very alluring, garbage collection. I know some hardcore low-level programmers out there will insist that garbage collection is never necessary, it's never a good idea. But whether or not that's the case, it's really hard to argue with the appeal. It shouldn't be surprising that the vast armies of people doing business CRUD applications wanted to stop thinking about memory management. Java also mainstreamed exceptions as the primary way to handle errors, and whatever problems this may have in practice, I think it definitely seems appealing. Because the alternative is ugly. The alternative is what we do in C and C++ of having to have an inbound error return value or saving to a global and checking the global after every time you do a call. It's not pretty. Golang with multiple return and that style probably is the better way to go. But that's not the solution Java came up with, and so it normalized this other thing that seemed better at the time. I think some people also came to like the subject-verb-object nature of method calls over straight function calls. Because, well, this is just what we do in English. It's subject first, then verb, then object. I myself don't find it all that appealing. I prefer consistency, and I think the distinction between subject and object in many, many cases gets very, very murky, which is one of the problems with object-oriented programming, as we'll get to. But this style of syntax in Java led to this convenience people, I think, since then have become addicted to, which is in their IDEs, it offers them, for this data type, what are my options? What can I do with this thing? It seems to enable a style of programming where you can just sort of browse. You don't have to hold all of the options in your head. You just have a vague notion of, well, yeah, I'm going to take that thing and transform it into this other thing. I don't remember exactly what the method's called. I'll just grope my way there using auto-completion in my IDE. Again, there's really actually no reason you couldn't have the same style of convenience in a purely procedural language. You would just have an auto-completion for, given this first argument, what functions take this type as its first argument. And it'd be effectively the same thing, really. But because of quirks of history and syntax design, this particular editing convenience has been implemented for languages like Java, but generally not straight procedural languages. And I think method auto-completion may actually largely explain why people sometimes claim that object-oriented APIs feel easier to use. It's because you can largely auto-complete your way through most of the usage. Another thing Java seemed to have going for it is that back in the mid-90s, this was the heyday of GUI programming, and it seemed really logical to map components as we see them in a GUI window and classes in an object-oriented program. That seemed like a very natural correspondence. This was the most tangible version of the real-world modeling which object-oriented promised. At the time, it seemed like a very plausible story, And on top of that, you have the virtue of Java being supposedly cross-platform with the Java Swing API, so you can write GUIs that will run on any system. They'll look horribly ugly, but at least, hey, they run on everything. You could do so-called RAD, rapid application development of GUI applications like you do in Visual Basic, except in Java, you're not locked into Microsoft's platform. So the funny thing to me about Java is that I think in an alternate history, it could have had virtually all the same success, if not even more perhaps, if it weren't object-oriented at all. It could have just been a straight procedural language and would have had still a big long list of attractive selling points. We could have had all the same portability, the same garbage collection, the same exception handling, and so forth down the line without any of the object-orientedness. Or at the very least, without forcing everything into the mold of classes. You could have it in a language like Python, say, where there are classes, but also just straight procedural code if you want, and they can live side by side just fine. So there still is this question. Java aside, there seems to be some appeal to object-oriented programming in itself, and what is that? Well, I think very simply, if you go back to the 60s and 70s, as people were grappling with the problems of software systems getting larger and larger, people tried to identify units of code abstraction that were larger than individual functions and data types. It's natural to want to describe any complex system in terms of large-scale components. If you talk about human anatomy, you don't explain it first in terms of microbiology. That would be nuts. We first talk about very major organs like the brain and the heart and the kidneys and so forth. As software gets larger and larger, it felt like these units of code we were building out of, the base materials, these data structures and functions, they became smaller and smaller relative to the whole. Sadly, though, the one general answer people could come up with of what is a unit of code abstraction bigger than a function and bigger than a data type is just simply a combination of the two, and hence objects were born. We took our functions and our data types and we associated them together into these larger units. We want to think in terms of paragraphs rather than individual sentences, and object-oriented programming seemed to have an answer for how we could do that. It's also very natural that as we build larger and larger systems and complex things, as much as possible, we want simple rote rules to guide us. Object-oriented programming seemed to present a unit of abstraction and a set of guidelines whereby we could incrementally accrete larger and larger systems. This line of thinking is what led us to patterns, and then the so-called solid principles and dependency injection and test-driven development, and all this stuff which has subsequently been piled on by many people who insist that this is now the one true way to do object-oriented programming. But to me, all these best practices represent band-aids. They are compensation for the fact that the original vision of object-oriented programming has never panned out, and every few years there's a new ideology in town about how we actually do object-oriented programming for reals this time. It's very easy to miss this dynamic. I know I did for several years, because I think within all of these addendums to object-oriented programming, there's lots of mystical speech dancing around genuine insights, but it's not quite cohesive. Object-oriented programming feels like this circle which we've been trying to square for over a generation now. Finally, let's talk about what's really wrong with object-oriented programming, specifically encapsulation, which is the linchpin of the whole thing. So consider, what is an object? An object is this bundle of encapsulated state, and we don't interact with the state of that object directly. All interactions with that state from the outside world come in through messages to the object. The object has a defined set of messages which it will receive, called its public interface, and so we have private information hidden behind a public interface. When an object receives a message, it may in turn send messages to other objects, and so we can conceive of an object-oriented program being this graph of objects all communicating with each other by sending messages. Many people today forget, though, that the original conception of a message is not exactly synonymous with just a method call. Yes, in practice it means calling methods, but a message, strictly speaking, sends only copies of state. It doesn't send references. A message sends and returns information about state, not state itself. And, well, wait a minute, objects themselves are state. And this has some interesting consequences. It means that, strictly speaking, messages cannot pass around object references. I've never seen a Java or C# codebase that ever follows this rule. Perhaps some Smalltalk programs have, but in general, this rule is not observed at all, and probably for good reason, as we'll discuss. But anyway, if we take the rule seriously, it means then for an object to send a message to another object, the first object must hold a private reference to that other object, because otherwise, how is it going to talk to it? To talk to an object, you have to have a reference to it. And where is an object going to get a reference to another object if it can't get object references from messages? The references which an object needs have to all be there at the object's inception. They have to be there for the whole lifetime of the object. And there's an even deeper consequence which is that if an object is sending messages to another, that other object is part of the first object's private state. And by the principle of encapsulation, an object should be responsible for all the objects which it sends messages to. And this should be obvious if you consider that messages indirectly read and modify state. When B sends a message to A here, it's messing with the state of A. Indirectly, sure, but it's still messing with its state. And so what happens when other objects come along and send messages to that same object, what's happening here? We have shared state. It's hardly any different than if you had a single global variable being shared by, say, 10 functions. If you have an object receiving messages from 10 other objects, those objects are all effectively tied together because they're implicitly sharing this state. Sure, the interactions with that state are indirect through public methods, but those methods are providing very trivial kinds of coordination of the state. You can impose rules through the accessor methods like saying, oh, if you access this field, it's a number, well, you can only increment that number. You can't mutate it in any other way. Fine, but this is a very trivial kind of protection. The hard problems of shared state are much, much deeper. Where in the system of 10 objects all sharing this state is the real coordination? And the answer is there isn't any. As soon as you have objects being shared, encapsulation just flies out the window. So if we're taking encapsulation seriously, the only real way to structure a program, to structure our objects as a graph, is not as a freeform graph, but as a strict hierarchy. At the top of our hierarchy, we have an object representing effectively the whole program. It's our God object. And that has its direct children, which represent the subcomponents, and those children in turn have their own subcomponents, and so on down the line. And each object in the hierarchy is responsible for its direct children. And the messages being passed strictly only ever go from parent to their direct child. The God object here, for example, is not supposed to reach down to its grandchild. It has to do all of its interactions with this grandchild indirectly through the grandchild's parent. Otherwise, who really is responsible for that object? Who's managing its state? It's supposed to be the direct parent. And so what happens when we have some sort of cross-cutting concern, like down in the hierarchy it turns out, oh wait, there's some business that object has with another object in a totally different branch of the hierarchy. How do they talk to each other? Well, not directly. Everything has to go through their common ancestor. For A to send a message to B here, it can't actually directly invoke any kind of method. It has to mutate its own state in some way, and then information about that state, that new intention of the object, gets returned from a message sent from A's parent. A's parent in turn, same thing has to happen, so it gets back up to the common ancestor, and then only finally when we get to the common ancestor can that intent be realized as a series of message calls, but not directly down to B. It has to be bucket brigaded down through the hierarchy. That is how you handle cross-cutting concerns in a strict encapsulated hierarchy. Obviously, no one writes programs this way, or at least no one writes whole programs this way. And for good reason. It's an absurd way to have to write your code. Now, you might argue that people do follow these principles in practice, they just do so inconsistently. And perhaps there is some value in a code base where you apply these principles inconsistently. Perhaps half-assed encapsulation actually gets us something. So imagine we have some sort of free-form graph of objects making up a program, and we decide, oh, well, there's this subsystem of objects that together should be their own self-contained encapsulated hierarchy of objects, and so we're going to refactor our code. Well, very often what that means is not only do we have to do a lot of complicated rethinking of the structure of the relationships here, of what calls what on the other objects, we very typically have to introduce more objects. Like say here, to represent this whole new subsystem, we probably have to introduce some new sub-God object, some ruler of this subsystem. Now, all interactions with this subsystem have to be reconceptualized as going through this minor deity. So say we successfully do this refactoring, and now while our code doesn't follow the principles of encapsulation perfectly, it's doing so in a half-consistent way, and maybe there's some benefit there. Well, I think what tends to happen is subsequently we decide, oh wait, we need some new interaction between elements of this encapsulated subsystem, and instead of having to do the hard work of figuring out how exactly it all gets coordinated from the root of that subsystem, the temptation is to just handle the business directly. But if we want to do the proper thing, we have two options. Maybe it turns out that that stuff external to the subsystem actually just needs to get integrated into that subsystem, and so it comes under the purview of the subsystem's root. But otherwise, we now have two subsystems that need to coordinate. And who's going to do the coordination? Well, now we need a new subsystem God object responsible for the collective business of these two subsystems. And now all interactions of these two subsystems have to go through this root object, but also all interactions with the outside world and these two subsystems have to go through this new root object. So as you can see, chances are really good that what you would actually do is say fuck it and just do this. You would just reach in and have the objects directly interact with each other, whether they should properly do so or not. And now, where's the encapsulation? What's the point? Whether you follow the rules strictly or loosely, you're in a bad place. If you follow the rules strictly, most things you do end up being very unobviously structured and very indirect, and the number of defined entities in your code base proliferates with no end in sight. The nature of these entities tends to be very abstract and nebulous, but alternatively, if you follow the rules loosely, what are you even getting? Why are you bothering? What is the point? When I look at your object-oriented code base, what I'm going to encounter is either this over-engineered giant tower of abstractions, or I'm going to be looking at this inconsistently architected pile of objects that are all probably tangled together like Christmas lights. You'll have all these objects giving you a warm, fuzzy feeling of encapsulation, but you're not going to have any real encapsulation of any significance. What people tend to create when they design object-oriented programs are overly architected buildings where the walls have been prematurely erected before we have really figured out what the needs of the floor plan are. And so what happens is, down the line, it turns out, oh wait, we need to get from this room over here to that room over there, but oh wait, we've erected barriers in between, so we end up busting a bunch of holes through all the walls, like the Kool-Aid guy, and the resulting pattern is really not organized at all, it's just Swiss cheese. We thought we were being disciplined, neatly modularizing all the state, but then the requirements changed or we just didn't anticipate certain details of the implementation, and we end up with a mess. The lesson we should take from this is to be very careful about erecting barriers, about imposing structure. It's actually better to start out with a free-form absence of structure rather than impose a structure that will likely turn out to not really fit our problem. Bad structure that doesn't really fit our problem not only makes it harder to implement the code in the first place, it hinders change, and it confuses anyone who looks at our code because it's implying one thing, but then what's really going on is another. In the object-oriented world, we have to think about all these graphs. We have to think about an inheritance hierarchy, we have to think about a composition graph, we have to think about data flows between the object, and also we're thinking about a call graph. The liberating thing about procedural code is there's just the call graph. We also, of course, do have to think about how our data is structured and how our data gets transformed throughout the course of the program, but the beauty of procedural code is that we can think about that totally independent of any notion of responsibilities. When I'm looking at my data, I can think just about my data, and when I'm looking at my functions, I'm not thinking about all these self-imposed barriers. I'm not constantly trying to group and modularize everything into these small units of so-called single responsibilities. When I sit down to write object-oriented code, I always have to play this game. I have this mental list of the obvious data types which my code will deal with, and I have this separate mental list of all the imagined behaviors I want in my program, all the functionality I imagine it to have. And then what object-oriented ideology demands is that I take all my behaviors and I somehow associate each one with one of my data types. Inevitably, what this means in any non-trivial program is I'm actually going to have to introduce all sorts of additional data types just to be these containers for certain behaviors which otherwise don't naturally fit with any of my obvious data types, the data types I knew I actually wanted because they represent actual data I need. In fact, as programs get larger and larger in object-oriented code, it tends to be that these unobvious, unnatural data types tend to actually predominate. You end up with majority of so-called data types which really aren't there because they're representing data. They exist simply as attacks to conform to this ideology about code modularization. Very quickly, we end up in what Steve Yagi called the kingdom of nouns, where every aspect of our program has to be reconceptualized as not just mere standalone verbs, functions. They have to be reconceptualized as nouns, things that represent a set of behaviors. And so what we get in our object-oriented code bases are all these service classes and manager classes and other what I call doer classes, these very nebulous and abstract entities. Even when dealing with data types and behaviors that are relatively concrete, which have fairly visible connections to the functionality apparent to actual users of the program, even here, the matchmaking game constantly presents us with these obnoxious philosophical dilemmas. In object-oriented analysis and design, we constantly have to ask ourselves stupid questions like, should a message send itself? Because maybe instead we should have some sender object which sends messages. Or wait a minute, maybe there should be a receiver object which receives messages, or a connection object which transmits messages. So very quickly, the real-world modeling which object-oriented programming promises becomes a fool's game, where there aren't any real good answers. In my experience, object-oriented analysis and design very quickly becomes analysis paralysis. If you take the ideology seriously as I did, you're going to waste a lot of time hemming and hawing about to conceptualize these elements of your program. Object-oriented programming is generally sold to students on the basis of these trivial examples that neatly model real-world taxonomy, but what we get in practice from object-oriented analysis and design is a lot of very abstract excess structure with no obvious real-world analogs. Note here that programmers have their own peculiar definition of abstract. When programmers talk about abstraction, they're generally talking about simplified interface over complex inner workings. What's odd about this is that in more general usage, abstract has a connotation of being hard to understand. Something which is abstract has no resemblance to the things of common daily life. And it turns out that most things which programs do are abstract in this sense. And so it shouldn't be surprising that we have great difficulty conceptualizing the components of a typical program in terms of neatly self-contained modules, particularly modules which have any real-world analog. When we pollute our code with generic entities like managers and factories and services, we're not really making anything easier to understand, we're just putting a happy face on the underlying abstract business, and for every excess layer of abstraction, we're getting more abstractness. In attempting to neatly modularize and label every little fiddly bit that our program does, we're actually just making our program harder to understand. Something that happens all the time when I look at object-oriented code bases is that I'll try and find the parts in code that correspond to some user-visible functionality. But trying to find the functionality going by clues from the names of classes and the names of methods tends to be very misleading. Very typically, my expectation that functionality X would be in the class named X turns out to be wrong, because the abstract nature of what we typically do in programs generally necessitates that functionality is not going to be self-contained. It's not going to neatly fit into one neat module. And so the class which is called X will very superficially relate to X, but then all the real work is done elsewhere, scattered throughout the code. This makes me question, what is the value of having a class called X if it doesn't really contain all the business of X? What this class X really represents is actually misleading code structure, and how is that helpful? How is that conducive to understanding of your code base? The other reason I have this problem reading code bases and trying to track down where functionality actually lives is because object-oriented design tends to fracture functionality in our code. It tends to take what otherwise could be relatively self-contained code and split it up into many separate methods across many separate classes, typically often in many separate files, for God's sake. This fracturing is accepted because of an ideology about encapsulation and this notion of classes and methods properly having so-called single responsibilities. And there are certainly valid arguments for that idea. Certainly it is much easier to get a small short function correct than to get a large sprawling function correct. But the important question is that in splitting our code up into many little small methods and to many separate classes, are we actually decreasing the total complexity of our program or just displacing the complexity, just merely spreading it around? In either case, there's this attendant trade-off we're making where by splitting up larger units of code into many smaller ones, we're greatly increasing the so-called surface area of our code, where I come along and I look at your code base and I try and get a foothold and everything's split up into these tiny little units, these tiny little packets of code. Reading this kind of code often feels frustrating in the same way it can be frustrating to eat a bunch of little candies that are all individually wrapped. And when all your methods are really, really short, you end up having to jump all around the code to find any line of logic. A lot of business that otherwise could be neatly sequentially expressed in longer methods gets artificially split up. So it feels like you've taken a neatly sorted deck of cards and thrown them into the air so you can play 52 card pickup. Okay, so if you're not going to be writing object-oriented code, what are you going to be doing instead? You're going to be writing procedural code, but what does that look like? Well, as I mentioned at the beginning, this doesn't necessarily mean you need to avoid classes entirely. If you have a language like Python or C++, where you have both straight functions and also classes, there are some cases where the association between your data types and certain functions is really, really strong, that it fits some organizational purposes to just explicitly associate them together by making those functions methods of that type. The most obvious example would be ADTs, abstract data types, things like queues and lists and so forth. The key thing to keep in mind, however, is that the moment you start hemming and hawing about whether this particular function really has a primary association with that data type, that should be the moment you say, screw it, we'll make it just a plain function. Because it turns out that most things we do in code tend to be cross-cutting concerns. They don't have necessarily special, obvious relationships with particular data types. They might concern more than one data type. And that's why you should generally prefer functions, so you don't have to play this silly game of matchmaking functions to data types. So we're going to be writing our code primarily out of plain functions, and we're not going to attempt to encapsulate the state of our program at a fine-grained level because it doesn't work. However, shared state is still a problem, and if we're not careful, it can get out of hand. We can't totally solve the problem unless we do pure functional programming, but short of that, there are broad guidelines we can follow to mitigate the problem. First off, when in doubt, parameterize. This means that rather than passing data to functions through global variables, you should instead make that data an explicit parameter of the function, so it has to get explicitly passed in. As much as possible, we want data access in our program to flow through the call graph. So anytime you're tempted to pass data to a function through a global because it seems more efficient or maybe just more convenient, you should give that a strong reconsideration. Secondly, whatever globals you do end up with in your program, it can be slightly helpful to group them logically into data types. Even if this means you effectively have a data type with one instance in your whole program, this little trick can often make your code seem just a little bit more organized. In a sense, you're just using data types this way to create tiny little sub-namespaces. But if you do a good job logically grouping your globals this way, as a side benefit, this can complement rule number 1, because now you can more conveniently pass this global state to functions. By bundling your data together into types, you typically cut down on the number of parameters which functions have to take. Though do be careful, there is an art to how you logically group things together. The third guideline is to opportunistically favor pure functions, even if you're not explicitly working in a functional style or working in a functional language. If you see an opportunity to make a function pure, it's generally a good strategy to take that opportunity. Again, pure functions tend to come at an efficiency cost, but the brilliant thing about pure functions is that they're the only truly self-contained unit of code. When I'm reading and writing a pure function, I don't have to think about anything else. I can just consider that function entirely unto itself. Therefore, they tend to be easier to understand and to make correct. The fourth guideline is that we actually should try to encapsulate our code, only in a very loose general sense at the level of namespaces, packages, modules, whatever your language has. So when I'm working in Golang, for example, I think of each package as having its own private state and then a public interface. I find that encapsulation at this coarse-grained level tends to work because you're typically dealing with much larger units of code than the supposedly ideal classes of object-oriented programming. The typical Golang program is going to have not that many packages, maybe like 10 at the high end, and structuring a mere handful of elements into hierarchy of encapsulation is reasonably doable. When it turns out during development that, oh wait, I have some cross-cutting concern of my packages and so we're going to need to violate this perfect hierarchy of encapsulation, again, it's not such a big deal because you're dealing with a relatively small graph of objects. All the basic problems of encapsulation are still there, it's just at the coarse-grained macro level, the problems are reasonably manageable. The last guideline is that you shouldn't be scared of long functions. For a long time now, programming students have been advised to, when in doubt, chop their code into smaller and smaller functions. But doing this has significant costs. There are trade-offs. It turns out that most programs have these key sections where most of what the code is doing is a long laundry list of stuff. And what we're told to do in these scenarios is write functions like this, where all the business has been extracted out to separate functions. The problem with doing this pervasively is that what was naturally a logical sequence of code and was otherwise written in sequence, top to bottom, is now spread and out of order throughout your code base. Obviously, in cases where the business extracted to a separate function is something that you want to call in multiple places, that's a very good reason to have a function. But if all these functions were just called in this one place, I would generally prefer looking at code where the business of those functions is just done in line. And if we want high-level documentation of what's going on in my func here, then you just put what I would call a section comment denoting what each section of the code does. In this arrangement, the sequence of the business is totally clear, and when I'm browsing the whole code base, when I'm looking outside this function, there's less clutter because there are now fewer functions I have to look at and wonder, well, hey, where is that called? I wonder what that thing does. It also has the advantage of letting us avoid having to name functions. Naming stuff is really important in code, but it's really, really hard to do well, and in general, I find it preferable if we can avoid naming entities as much as possible. In this arrangement, we don't have to think hard about what to call these functions. We can just have a comment line and have a full English sentence, which generally is better at conveying accurate meaning and also is simply easier to write. If, for whatever reason, it doesn't seem adequate to simply comment a section rather than extract it to a separate function, the next best thing is to make it a private function, a nested function, such that it's clear this function is not called anywhere else, it's only called within this function. In this arrangement, I, as a reader of your code coming from the outside, I'm still presented with a smaller surface area, fewer entities in the code, and so it's just easier for me to get a foothold. Now, when you do write functions which are hundreds, if not thousands of lines long, you still should keep in mind general guidelines about code readability, basic things like not straying too far from the left margin for too far or for too long. You don't want to have code that's indented in 8 levels because it gets really obnoxious scrolling up and down code if you have to scroll over for one thing. And also it tends to just imply there's a lot of busy logic in this part of code and it gets confusing. So likewise, you also need to look out for parts of functions where the logic's just getting too complex. The first thing to do is, of course, to try and simplify your logic But failing that, there are going to be cases where, hey, we should just split this off into a separate function so it's more neatly self-contained complexity. The other concern with longer functions is that as your function gets longer and longer, you tend to accrue more and more local variables. So what you want to do is, hopefully your language allows this, you want to try and constrain the scope of the local variables so that they don't exist for the full duration of the function, but rather for subsections. This way, I, the reader of your code, when I scan up and down the function, I don't have to think about all the variables for the whole duration of the function. The way this is done in most curly brace languages is you can just introduce a new subscope with curly braces. So here, for example, this integer x variable only exists within these curly braces. When you have subsections of a function which you are commenting, it's generally a good idea to, when in doubt, enclose them in curly braces. This gives readers of the function an assurance that variables from the preceding sections don't fall through to the following sections. And so in later sections, we don't have to think about the variables that were used above. Where possible, the even better thing to do is to enclose these local scopes in their own anonymous function that's then just immediately called. And the advantage here within the nested function is that it's not just its own subscope, but also within this anonymous function, it's guaranteed that any return is not going to return out of the enclosing function, it'll return just out of this enclosed function. And so we have a stronger guarantee that the logic of this subsection is self-contained from the enclosing function. Unfortunately, what I often really want when creating subsections of longer functions is a feature that doesn't exist in any language I know of. It's an idea I've only seen in one other place. It was Jonathan Blow in his talks about his programming language that he's making. And the idea is that we want something like an anonymous function which doesn't see anything of its enclosing scope. The virtue of extracting a section of code out to a truly separate function is that everything that comes into the function has to be explicitly passed to a parameter. It would be great if we could write inline anonymous functions with this same virtue. Specifically, what I would propose is imagine we had a reserved word use that introduces a block, and in the header of the use, we list variables from the enclosing scope which we want to be accessible in this block, but otherwise anything from the enclosing scope would not be visible. These listed variables, however, would really actually be copies of those variables. So if you assign to x or y here in this scope, you're assigning to x and y the local variables of this use block, not to x and y of the enclosing scope, which is the effect you get with a truly separate function, right? You assign to the parameters of a function. You're not modifying what was passed to the function, you're just modifying those local variables. That's the same thing we want in this use block. Furthermore, a use block should itself return values. So you use return inside the use block, and it doesn't return from the enclosing function, it returns from the use itself. The use is an expression, and so we can return values from this use and assign it to this variable a. So in effect, we'd have this block of code which is as neatly self-contained as a separate function. However, it is written in line, and so it's very, very clear that, oh, this is a piece of code that's only used in this one place. You don't have to go look for it elsewhere. And also, we don't even have to give it a name. Instead, we can just put a section comment header before the use block, and that is generally much better for containing the actual intent of this block of code. If later down the line we decide that this block of code actually should be extracted to its own proper function, that's a very easy thing to do. You can have an editor convenience that does that for you automatically. It's already clear what the parameters and the arguments should be. All the programmer would have to do is provide a name for the new function. So anyway, it'd be nice if languages had this feature. Unfortunately, I don't know of anyone that does. But regardless, you shouldn't be so scared of long functions. They actually have their place in most code bases. At the very least, I hope I can get you to try procedural programming. It doesn't really matter what language you're in. If you're in Java or C#, you can write procedural code, you can break the rules. But if you've ever felt any of the paralysis that I felt attempting to do object-oriented programming properly to square the circle, I think you'll find abandoning all those ideas and just reverting to procedural code to be a liberating experience. I can tell you from personal experience of having read these books that you don't need to read them. They don't have answers, they're not going to square the circle, and you're going to waste productive years of your life trying to live up to their ideals. I'm not saying there's nothing to these ideas. There are bits and pieces that have value. Test-driven development, for example, has some interesting ideas. There's value in testing. But that's part of the problem, is that kernels of good ideas have been taken to holistic extremes in a way that I think has been disastrous for the industry and certainly for programming education. There are very few solid holistic answers about how we should write code. We'd all be better off if we stopped chasing that chimera.